Jackie, Alexis, Jose, Yaritza, Juan. All right, let's go ahead and get started. The first question, what is an arithmetic sequence? So what makes an arithmetic sequence a sequence? Because a sequence is just a sequence of numbers, but what makes it arithmetic? What's the relationship between the numbers if it's an arithmetic sequence?
Isn't there a pattern?
There is a pattern, for sure.
It could be like an increase in pattern by 1 or something. Or
Yeah, that's an
multiplication by
example.
2,
It could be increasing by 1.
or multiplication by 2.
Right, so arithmetic means that you're always adding by the same number or subtracting by the same number. So there's a common difference. So I'm going to start record keeping up here. So with an arithmetic sequence, you are always adding or subtracting by the same amount every single time, which means that you have a common difference, which we denote by the letter D. All right, so that's what an arithmetic sequence is. And then what is the formula? The formula, that is for an explicit formula. So if you want to know explicitly, let's just take a simple example of an arithmetic sequence, like counting by 2s starting at 6. So 6, 8, 10, 12, 14. So that's an arithmetic sequence. You're counting by 2s. And if you want the explicit formula, then it's what formula will give you the nth term. So a sub n represents the nth term of your sequence. And it's the first term plus the common difference times n minus 1. So that's your explicit formula to completely determine the whole sequence. If you want the 100th term, just plug in 100 for n there, and you can calculate the 100th term in the arithmetic sequence. So that's arithmetic. Okay, so what's a geometric sequence? What's the difference there? What is a geometric sequence compared to a arithmetic sequence? Yes, Michael? What?
Does it have a
Yeah, sorry, Michael, Emmanuel. Yeah, it has a common ratio. So here we're going to multiply or divide by the same amount every single time. And that is a common ratio, which we denote by the letter R. And so a sequence, a basic one, say multiply by 2, so 1, 2, 4, 8, 16, 32, and so on. And then what's the explicit formula for that? The explicit formula. What's the explicit formula for a geometric sequence? Austin, you have it on your notes?
I do, yeah. It is a n plus 1 equals r times a n.
Ooh.
I would say that.
That sounds very similar to the formula I'm thinking of, but so you had a sub n, so the nth term is equal to what?
R times a. Or am I just looking at the wrong thing?
You might be looking at the implicit formula rather than the, yeah, you're looking at the implicit.
Okay.
But somewhere on that page, we wrote down that it's the first term times the common ratio to the power of n minus 1. Okay, so there we go, folks. We have essentially this knowledge. There are a few other formulas that we might need, but this is definitely the beginning of it. Okay, and then what's the difference between an explicit formula and an implicit formula? So for instance, now that we've seen the explicit formulas, here's your implicit formula. So for arithmetic, it's a sub n equals the previous term plus d. So that's your implicit formula for an arithmetic sequence. And it says that if you want the nth term, you need to know the previous term. So in order to calculate any given term, you need to know the term before it. And so this formula might seem a little more laborious because in order to know the 100th term, you have to know the 99th term, which means you have to know the 98th term. So you have to calculate your whole way there. But some formulas, that's actually easier than figuring out an explicit formula. Whereas here, the implicit formula for geometric would be that the nth term is equal to what? Oh, r times the previous term. So just as an example, last class we ended by talking about the Fibonacci sequence of rabbits and how rabbits multiply at a very rapid pace. I'm sure there are other animals that multiply at a rapid pace. But the Fibonacci sequence was 1, 1, and then you add the two previous terms. So 1 and 1 is 2, 1 and 2 is 3, 2 and 3 is 5, 3 and 5 is 8, and so on. And we said that the formula, the implicit formula, was a sub n is equal to the previous term plus the previous term. And see, that's a very simple formula. So defining the Fibonacci sequence implicitly is actually very simple to do. You say, add the two previous terms. Whereas look at the explicit formula for Fibonacci. This is quite a surprising formula. Here it is. This is Fibonacci's explicit formula. So let's see there. The nth term is 1 plus root 5 over 2 to the power of n minus 1 minus root 5 over 2 to the power of n all over root 5. Well, that's terrible. This is a very inconvenient formula. I mean, just imagine plugging 1 into it just to get the first term. What should the first term be equal to? 1. And so what do we need to do? Plug 1 into that mess? Look, if I just plug in 1, that would give me 1 plus root 5 over 2 to the first minus 1 minus root 5 over 2 to the first all over root 5. And so now I have to distribute this minus sign. That gives me all over 2. So that's 1 plus root 5 minus 1 minus a negative plus root 5. Oops. And then all over root 5. So the 1's cancel out. And then I have 2 root 5. Wait, do I really? Over 2 over root 5. So then the 2's cancel out, and then the root 5's cancel out, and it equals 1. Ooh, that's a laborious formula. So I share that with you out of interest, because it's an interesting sequence, the Fibonacci sequence. You hear it a lot in common culture. Well, okay. Do you hear it a lot in common culture? I mean, maybe it's not in every TV show you see, but you will see the Fibonacci sequence out there. And the implicit formula in that case is very, very easy, whereas the explicit formula is very, very hard. So in that case, you know, if you wanted to know, say, the 20th term in the Fibonacci sequence, it would be very easy to find the 20th term by adding the two previous terms. Whereas plugging a 20 into that, woo, like you'd really need a calculator to do that. All right. Well, I can tell you're all wowed and impressed by that distinction between an implicit and explicit formula for the Fibonacci sequence. So let's keep going. Today is what, November 26th? It's my mom's birthday. Please make sure you all send her a text or an email. She's expecting it. All right, and we're going to cover 9.2. And let's see. Oh, no, I already told you both of those jokes. I need to give you a new joke. I'll tell you the joke that my daughter just learned, because I'm trying to teach her jokes. So what did one snowman say to the other snowman? Smells like carrots. And then even better, I taught her the joke, where does the king keep his armies? I think we already did that one. Where does the king keep his armies? The answer to the joke is in his sleeveys. right? She says, where does the king keep his armies? She says, in his sleeves. Very funny. All right, well, here we go, folks. Section 9.2, this is our last section of new content. Very exciting. I want you to know how exciting that is, that you have so many days ahead of you before your next test, before your final exam, and this is your last day of new content. I've been in a math class where we got new content the day before the final. What? New content the day before the final? That's crazy. So you really are blessed, right? That you have, today's your last day of new content, and then you have lots and lots of days to review for the next test, review for your final exam. This is a very, very cushy situation. Now, I realize you're probably in 2, 3, 4 other classes. So I realize that probably just barely makes life bearable. But just remember, you have lots of days before your test and before your final exam. All right, so 9.2 is called summation notation, which kind of sounds like conjunction, junction, summation notation. So summation, what does the word sum mean? Yeah, add them all together. Summation is add them all together. And we have this notation here with this Greek letter right here. Does anyone recognize that Greek letter? What Greek letter is that?
Sigma.
Yeah, sigma. That's the Greek letter sigma. So in the Greek alphabet, the capital letter S is called sigma. And then what's the lowercase sigma? Isn't that it? The lowercase sigma? Well, anyway, Greek, you've got upper and lowercase. So the uppercase S Greek letter is sigma. And they use the letter sigma because it has the same first letter as the word sum. I suppose that's the main reason why they use the symbol. Also, it's very convenient for how we use it, such that the term to the right is, of course, what we're calling the nth term. So that's the formula for the nth term. They write a sub I instead of a sub n, but it's still the formula for the nth term. And then down below is the term that you start with, and then up above is the term that you end with. So at first glance, that might seem a little confusing, so we'll definitely jump right in and do an example. Let's look at this example first, and then we'll go back and read all about it. So find the value of each sum. So number 1, we've got sigma here, meaning take the sum, where you start by letting g equal 4, and you run all the way up to 9. So you're going to let g equal 4, 5, 6, 7, 8, 9. In the expression 5g plus 3. So what they're saying is that this right here is our nth term formula. Nth term formula. That's how you calculate all of your terms. Which, in and of itself, if that was our nth term formula, like let's say I called it a sub g equals 5g plus 3, I could just go ahead and calculate as many terms as I like. So for instance, the first term would be 5 times 1, which is 5 plus 3 is 8. And the second term would be 5 times 2 is 10 plus 3 is 13. And the third term would be 5 times 3 is 15 plus 3 is 18. And at that point, well, maybe one more if you can see the pattern. A sub 4, 5 times 4 is 20 plus 3 is 23. And do you all see the pattern now that I could just keep writing these terms down? 8, 13, 18, 23. So the next one would be 28, and then 33, and then 38, and then 43, and so on. So that's what this formula represents. It's simply the nth term formula. You'll notice it can be a sub g equals 5g plus 3, a sub n equals 5n plus 3. It doesn't matter what letter you're using. It's still the nth term formula. And so what do they want? Let me finish this off. A sub 5, a sub 6, a sub 7, a sub 8, a sub 9 would be 48. So I just happened to write down the first 9 terms just so you can see what this sequence looks like. And what they're saying here, if you want to write it in English, is find the sum of, we're going to do a sub 4 plus a sub 5 plus a sub 6 plus a sub 7 plus a sub 8 plus a sub 9. That's what they're asking us to do right there in that very concise language. They're saying sigma, find the sum of this term formula, 5g plus 3, starting with the 4th term, ending with the 9th term. So you could even put a little th there. That's your 4th term, that's your start, and the 9th term, that's your end. So you start with the 4th term and you end with the 9th term. What's strange about that notation? Don't say everything. Maybe is it strange that you read from bottom to top? Maybe, I mean, we typically read books from top to bottom, so maybe it would have made more sense to start on the top and end at the bottom. Might make you wonder, well, gee, why did they do that? I have no idea. I've never looked that up. Historically, I'm sure there's a good reason why they started at the bottom and end at the top. But hopefully the fact that the numbers go in order makes it more obvious that you're starting with the 4th term, ending with the 9th term, and adding everything up in between. Okay, so what can we do now to write this down nicely and neatly? The first thing you could do is go ahead and say literally what they're asking for, which is they're asking for the 4th term plus the 5th term. Actually, I'm going to spread this out a little bit. They're asking for the 4th term plus the 5th term plus the 6th term plus the 7th term plus the 8th term plus the 9th term. So I'm going to show my work downward. So I hope you show your work similarly. Well, so what is the 4th term? The 4th term is going to be this structure 5g plus 3 where I put in the number 4. So the 4th term is going to be 5 times 4 plus 3. And then the 5th term is going to be 5 times 5 plus 3. And the 6th term is going to be 5 times 6 plus 3. And the 7th term is 5 times 7 plus 3. And the 8th term is 5 times 8 plus 3. And the 9th term is 5 times 9 plus 3. Now I realize that by writing all of that down right now, I've already lost a couple of you. Like, oh, I don't want to write all that down. I don't know how that ever became a thing in mathematics that people are like, oh, I don't want to write down all that work. Folks, it's just part of life. Part of life is you just write a lot of things. Right? There's a lot of writing involved. Be like if you're in an English class and they're like, okay, you have to write a 5-paragraph essay, and you're like, I only want to write 1 paragraph. You know, that's not how it works. It's long. You write it down, and there's many, many steps. So the sigma notation, that's what it means. This is now substituting my values. Now I can go ahead and add all those. And by the way, I already knew what these were. My 4th term was 23, but I'm going to go ahead and calculate anyway. So 23 plus 28 plus 33 plus 38 plus 43 plus 48. Now at that point, you'd probably just plug that into your calculator. You just plug that into your calculator. Although, much like the story that we read about Gauss, the childhood Gauss, when I think he was like 5 years old, he added up the numbers 1 through 100. You could add these up fairly conveniently by doing some clever grouping. So for instance, each pair has a 3 plus 8, a 3 plus 8, and a 3 plus 8. So 3 plus 8 is 11, and there's 3 of them. So already I know that's 33. And then I have 2 20s, that makes 40. And I have 2 30s, that makes 60. And I have 2 40s, that makes 80. And so now I'm here, 40 and 60 is 100. And then 80 and 33 is 113. And that gives me 213. So I just show that to you because that's how people do mental math. That's how people come up with answers to large sums like that, is they would essentially do all that in their head. So our answer is 213. I guess my point is people would not just add them term by term by term. That's not what mathematicians do. They would say, okay, 23 plus 28, that's 51, plus 33, that's 84, plus 38, that's my brain hurts. You know, it gets tiring if you do it just linearly. You'd want to chunk it up into chunks. Okay, well, so that's sigma notation. Let's go back and read it now. We've got this summation notation, otherwise known as sigma notation. Summation notation or sigma notation represents the summation of terms generated from a formula. The summation symbol is the capital Greek letter sigma. I is the index. So in that case, they're using I to represent the index number. That means like the 4th term, 5th term, 6th term, 7th term, 8th term, 9th term. That's the index they're referring to. A sub I represents each successive term, so the ith term. M is the lower bound of summation, and N is the upper bound of summation. As we said, you're going from bottom to top. Yep, that's sigma notation. So you're probably already looking at number 2, and you're saying, so first of all, which terms are we adding together? We're going to start with the 1st term and end with the 4th term. So we can already go ahead and write down that I'm going to do the 1st term plus the 2nd term plus the 3rd term plus the 4th term. And maybe that seems really obvious to write that down, like Mr. G, I'm not even going to bother writing that down. But see, it's so helpful. It's so helpful to your brain. It's so helpful to your audience to just write that down so you can see. And again, you should spread it out because we're about to put a lot of structure underneath each of those terms. So what is our structure? Each term is 1/4 I squared plus 1. That's what each term is, 1/4 I squared plus 1. So with my first term, it would be 1/4 1 squared plus 1. And my second term would be 1/4 2 squared plus 1. And the third term is 1/4 3 squared plus 1. And the fourth term is 1/4 4 squared plus 1. Do any of you remember watching The Karate Kid? I mean, that was a long, long time ago, I guess in the 80s when The Karate Kid first came out. I think since then they've come out with more and more Karate Kids. And there's even a TV show that follows, what's his face? The guy from the dojo, the bad one. Well, anyway, if you recall in The Karate Kid, what did Daniel LaRusso, what was Mr. Miyagi making Daniel LaRusso do all the time? He had chores, right? He made him paint his fence. He made him sand all the decks. He made him wash all of his cars. Seems very kind of lame. But all of that builds discipline, like the ability to stick with a very monotonous, mind-numbing task. And believe it or not, that's a skill that you learn in a math class. How to stick with a monotonous, mind-numbing task. That's an important skill to have, is the patience to complete a monotonous, mind-numbing task. And that's what this is. By writing all this down, the skill you're really demonstrating is patience, as well as arithmetic. Okay, so now folks, this 1/4 going all the way across, what can we do clever with the 1/4?
You can take out the 1.
Yeah, can we factor out the 1/4 and just put 1/4 at the very beginning? And then we can just write down the terms that we have inside. So now we can say 1 squared is 1 plus 1 is 2, and 2 squared is 4 plus 1 is 5, and 3 squared is 9 plus 1 is 10, and 4 squared is 16 plus 1 is 17. And so now we just have 1/4 times 2 plus 5 plus 10 is 17. That's allowed. As I said, one thing mathematicians like to do is clever regrouping to help make your addition go more simply. Because otherwise, if I hadn't pulled out that 1/4, we would have had the terms 2/4, 5/4, 10/4, and 17/4, which is immediately not as attractive to about anybody. Whereas by pulling that 1/4 out, you got to stick with whole numbers on the inside. Okay, so now what does that give us? 2 and 5 is 7, plus 10 is 17, plus another 17 is 34. So that's 1/4 times 34, which is 34/4, or 17 halves, or 8.5. Yeah. Just another thought about how mathematicians think. 1/4 and a 34, that's basically the chain of reasoning. You'd say, okay, well, 1/4 times 34, that's 34/4, I can start reducing that. And then, you just do these teeny tiny little calculations to baby step you to the answer, rather than actually trying to do 34 divided by 4, right? Because then you're like, oh, okay, 34 divided by 4, 4 goes into 3, it doesn't. 4 goes into 34, I guess 8 times 8 to 4 is 32, subtract, drop the, okay, right, like that's a much longer process. It's harder to do in your head. Whereas simplifying something like this is easier to do. All right. Third example on this page. What is this notation? It's an exclamation point. Are they just really excited? Do you remember seeing the exclamation point notation before? Maybe a long time ago in your past? Let's make a note about what it is. It's called factorial. So an n factorial, pronounced factorial. Although if you're at a math party, you could be clever and say something like n. But that's not really what anyone does. They would say n factorial. You wouldn't say n exclamation point. You'd say n factorial. And n factorial, probably easier to give the definition with an example. 5 factorial is equal to 5 times 4 times 3 times 2 times 1. So you multiply all the integers together in a downward succession. So 4 factorial would be 4 times 3 times 2 times 1. And 3 factorial would be 3 times 2 times 1. You're just counting down. So 2 factorial would be 2 times 1. 1 factorial would be 1 times 1. So whatever number you start with, you just start counting down and you multiply all together. By definition, we mathematicians define 0 factorial to be equal to 1. That might feel a little strange, because 0 factorial, you would think you'd say, okay, well, you start with 0 and then count down to 1. But if you count down from 0, you'd go to -1 and then -2. That doesn't make any sense. So rather, mathematicians define 0 factorial to be equal to 1. The formal definition of factorial would be n factorial, which is n times n minus 1 times n minus 2, dot, 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 all the way down to 3 times 2 times 1. That would be the technical definition, but a lot of times that can look a little confusing. You're saying you're starting with the first number n, and then you go to the number smaller than that, which is n minus 1, times the number smaller than that, which is n minus 2, and it would just keep going like that for a while, times n minus 3, times n minus 4, but eventually you'd get all the way down to the numbers 3, 2, 1, and then you're done. So that's the formal definition of n factorial. So now that we've seen that, we can go ahead and compute this summation. Which terms are we going to add together in this summation notation? Now, from the first term to the fifth term, so we could go ahead and write out the first term plus the second term plus the third term plus the fourth term plus the fifth term. I know those are the terms I'm adding up. And so now it's a matter of just plugging in our values, 1, 2, 3, 4, 5. So if I start by plugging in 1, that would give me 1 plus 1 is 2 factorial over 1 factorial. And then I plug in the number 2, so that would give me 2 plus 1 is 3 factorial over 2 factorial. And then I plug in the number 3, so that's 3 plus 1 is 4 factorial over 3 factorial. Plus the fourth term, I plug in 4. 4 plus 1 is 5 factorial over 4 factorial. And then the fifth term, I plug in 5. 5 plus 1 is 6. 6 factorial over 5 factorial. In math, you often come across expressions that look strange or confusing. Like, well, geez, what do we do now with 3 factorial over 2 factorial? Or what do we do with 5 factorial over 4 factorial? The first thing you might say is, can I reduce any of those fractions? So first of all, are any of those fractions simplifiable? No, they're not, which will never be the case because the numbers are always apart by 1. If you take any number, like 16, and take the number 1 below it, 15, they will never share any factors, and it's never simplifiable. So first of all, the fraction's not simplifiable, nor are we even allowed to simplify them because of this factorial symbol is telling us to do something. So how do we calculate this? Let's start with this one. We'll just jump right to the hardest one. What is the answer of 6 factorial divided by 5 factorial? We're not sure. But we could start by saying, well, I've got 6 factorial, which is 6 times 5 times 4 times 3 times 2 times 1, which is what? 2 times 3 is 6, times 4 is 24, times 5 is 120, times 6 is 720. And then 5 factorial is 5 times 4 times 3 times 2 times 1, which was 120. And then what's 720 divided by 120? 6. Now the good news is you don't have to do any of those calculations because look back at what I wrote down originally. What can I do to that whole fraction now? What can I do to the top and bottom? I can cancel lots and lots and lots. I can cancel the 5, the 4, the 3, the 2, the 1, and the answer is obviously 6. Without doing all of those computations. So 6 factorial over 5 factorial is just 6. So likewise, just imagine in your mind, what's 5 factorial over 4 factorial? You'd write out the 5, 4, 3, 2, 1 over 4, 3, 2, 1, and all those terms are going to cancel except for the 5. So now we can see what to do for each of these terms in terms of doing the quick calculation. It's just 2 plus 3 plus 4 plus 5 plus 6. Which again, if you do grouping, you'd say, well, 2 plus 3 is 5 plus 5 is 10, so that's 10. 4 plus 6 is 10, so that's another 10, so 10 and 10 is 20. And again, that's called grouping, adding by grouping. Not many mathematicians would just plot along in order saying, well, 2 plus 3 is 5, 5 plus 4 is 9, 9 plus 5 is 14, 14 plus 6 is 20. People don't really do that. You group the numbers together in a way that's convenient. All right. So, especially looking at this example, is sigma notation hard? No, did this problem look hard? Yeah, it looked really confusing at first glance. But in fact, the computations were actually very simple. The definition of factorial was very easy to use. And in the end, the answer was just 20. It was a very simple problem. It just looked hard. Right? That's another vast life lesson about mathematics. It just looks hard. Once you know how to do it, it's pretty simple and straightforward. But it does look hard at first. I don't know if that helps at all. I'm like, yeah, math only looks hard. You're like, no, Mr. G, actually, sometimes it is hard. Well, that's true. Sometimes it is hard. All right. Well, that's sigma notation. What else do we have here? Because we're talking about adding things together, there happen to be some summation formulas that allow us to actually add sequences together pretty quickly without having to actually list it out. So what you all just did right there was adding together a sum by brute force, by actually listing out each term and adding them all together. In fact, we have these nice formulas that allow us to do sums very quickly without having to actually list out all the terms and add them together. So let's add this to our notes then. Actually, I'm going to put it here in the margin. So for an arithmetic sequence, my sum is the sum of n terms is the number of terms over 2 times the first term plus the last term. I would write all this down in your own handwriting, just kind of in the margin somewhere, just to put it in your own handwriting. So the sum of an arithmetic sequence, this means the sum, capital S, of n terms. And by that we mean terms beginning with the first term. So you're going to add the first term plus the second term plus the third term plus all the way up to the nth term. So when we say S of n, now we're saying that we always start with the first term. We're going to begin at the beginning of the sequence. And the sum of those n terms is just n over 2 times the first term, so that a sub 1 represents the first term. And a sub n does normally represent the nth term. And since we're saying that there are only n terms in the sequence, this a sub n actually represents the last term that we want to add up. So if we want to add up 10 terms, they're saying take the first term plus the 10th term, add them together, and then multiply by 10 over 2. So that's the arithmetic formula. There's also a geometric formula where they're saying the sum of the first n terms is the first term times 1 minus the common ratio to the power of n all over 1 minus the common ratio. Now you might look at these formulas and say, what? Where do these formulas come from? And the thing is, we just get to inherit these formulas. You know, previous mathematicians came up with them, they proved that they were true, and now we just have these nice formulas that are just sitting there waiting for us, and we just get to use them. So that's our geometric sequence sum. And then there's even a formula for finding the sum of infinitely many terms. That's what that S sub infinity stands for. That if you're looking at a geometric sequence, you can actually find the sum of infinitely many terms by simply taking the first term and dividing by 1 minus the common ratio. And that is provided that the common ratio, the absolute value of the common ratio is less than 1. And what that really means is that the value of R has to be somewhere between -1 and 1. So the common ratio has to be a fraction. Like if you're multiplying by a half over and over and over again, or multiplying by a third over and over and over again. So you can only add up infinitely many terms of geometric sequence if the common ratio is a fraction, like 1/2, or 3/4, or -1/3, or -7/8. That's the only time that you can actually find a sum of infinitely many terms is if it's a geometric sequence and the common ratio is strictly a fraction between -1 and 1.
I have a question. Is
Yeah.
that the absolute value?
Yeah, absolute value means,
It's only positive.
no, it means that the absolute value of r is less than 1. So for instance, if r was -7/8, so let's do that. Thanks for asking. If r was -7/8, and I want to find the absolute value of r and say that it's less than 1, what's the absolute value of -7/8?
It's gonna be positive.
There's 7/8, and is that less than 1? Yeah. So they're not saying r has to be positive. They're saying that whatever r is, if you take the absolute value, it's less than 1.
Okay, so can we turn it to positive?
Say that again louder.
If it's a negative number,
Yeah.
mean negative number, it will automatically become positive because it's in its absolute value.
Yeah. To tell you the truth, it's a little unfortunate that they express it in this way. The absolute value of r is less than 1. It would be much nicer to most people if they wrote r has to be between 1 and -1. See, isn't that much nicer? R has to be between 1 and -1. That's a much more user-friendly way of saying the absolute value of r is less than 1. We're just saying that r has to be between -1 and 1. Is that better, Annabelle? Okay. All right, so we're talking about taking sums. Sigma notation was taking the sum the long way by brute force, by actually computing every single term and then actually adding them all together. Whereas now this section is talking about how can we find a sum without actually knowing what every single term is and adding them all together by brute force. It turns out there is a formula. All right. So the first thing you might be wondering is, I have a formula for arithmetic sequences. I have a formula for geometric sequences. How do I know if this is arithmetic or geometric? How do I know which formula to use? So is this sum arithmetic or geometric? Is the sequence arithmetic or geometric? How do we know? Are we adding a number every time, or are we multiplying a number every time? What's that, Tanya? We are adding a number every time. How do you know that? Plus sign? Okay, very nice. There's plus sign there. How can we convince ourselves that this is actually an arithmetic sequence? It's very simple to do, but it requires effort. Just start writing out the terms. Right? They gave us a formula. Remember, this is always the formula for the nth term. So we could just go ahead and start writing out terms and then just look at the sequence, right? What better way to know about the sequence than to look at the sequence? So we're doing the first term through the 10th term, and that's our formula. So I could just go ahead and write out the sequence, the first few terms anyway. The first term would be 5 times 1 is 5 plus 3 is 8. The second term is 5 times 2 is 10 plus 3 is 13. The third term is 5 times 3 is 15 plus 3 is 18. And the fourth term is 5 times 4 is 20 plus 3 is 23. And so just by looking at the first few terms, you should be able to convince yourself if it's arithmetic or geometric. So it just requires a couple seconds of extra energy to just write out the first few terms. And sure enough, what are we adding by every time? We're adding by 5. Now that you know we're adding by 5 every time, why is that obvious in the formula? Do you see the 5 in the formula? Yeah. And in fact, I just mentioned it in passing last time, that in an arithmetic sequence, the number in front of the variable is the common difference. So, for instance, this 5n plus 3, that looks a lot like mx plus b. It is, in fact. And that m is actually the common difference. So in linear equations, the m is the slope. In arithmetic sequences, the m is actually the common difference. So the common difference is 5, and this is indeed an arithmetic sequence. Now, we'd still like to find the sum of the first 10 terms. And at this point, we've already started. The pattern's pretty obvious. The numbers end in 8 and 3. I could go ahead and finish writing out the sequence and add them together by brute force. But in general, I don't think too many people want to do that, add them together by brute force. Because what if that was 100 instead of 10? Would you really want to sit there and add them all up? I mean, technically, it'd be easy to do. Anybody could do it. You could train a child to do it using a calculator. But nobody actually wants to sit there and add all those up. It's enough for us to know that this is an arithmetic sequence, and the common difference is 5. So let's look back at that formula. We have our formula for an arithmetic sequence. What do we need to know in order to calculate the sum? We want the sum of the first n terms. How many terms are we doing? 10. So I know that we're doing n equals 10. The formula itself says n over 2 times a sub 1 plus a sub n. What does a sub 1 represent? The first term, which I already know, it's 8. And what is the nth term in this case? The 10th term. Do I know the 10th term? I don't know the 10th term. So how would I find the 10th term? I could always just finish writing down the sequence. So it's 8, 13, 18, 23, 28, 33, 38, 43, 48, 53, 58. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 53 is the 10th term. Now again, what I just did was I brute forced it. You know, I wrote down the terms and I found the 10th one. Would I have done that if they were asking for 100 terms? Definitely not. That would have taken a really long time to write down 100 terms. So instead, what we can do, if we need to know the 10th term, is go ahead and compute it. We have a formula, a sub n equals a sub 1 plus d times n minus 1. We can find the 10th term. So let's find the 10th term, that's the first term, plus the common difference, which is 5, times 10 minus 1, which is 9. Sorry, 10 minus 1, which is going to be 9. And so the 10th term is the first term, which we already know is 8, plus 5 times 9. So 5 times 9 is 45, plus 8 is 53. Okay. So that gave me the same answer, the number 53. Now what have we done so far? Did we find the sum of the first 10 terms yet? No, we haven't even done what the problem asked us to do yet. What have we been doing? We've just been spending time getting to know the sequence. That's actually a really valuable, vital part of math, is just spend some time getting to know the problem that they're telling you to solve. So what they really want us to do is add up the first 10 terms, and there they are. Those are the first 10 terms, and they want us to add them up. And what we've done so far is we've just investigated this sequence. We wrote down the first few terms. We said, hey, it's an arithmetic sequence. We're adding like 5, so that d equals 5. In order to do that summation formula, we need to know n, a sub 1, and a sub n. So n is 10 terms, a sub 1 is 8. We knew that from just writing down the sequence. And a sub 10, we got that by using the explicit formula. Okay, so we've spent a lot of effort just getting to know the problem. Now we're in a position to actually solve the problem. That's a huge aspect of math. I feel like I'm talking a lot about math in general today. But this is all good psychological information to know about what it's like to do math. You have to spend some time getting to know the problem, spend some time understanding what it's saying, and then finally you can just write down the formula, which is S sub n equals n over 2 times a1 plus a n. Now we're finally in a position to just use that formula. So let's fill it in. The sum of the first 10 terms is 10 divided by 2 times the first term plus the last term. You'll notice that by the time I actually wrote down the formation, for the formula for the sum of an arithmetic sequence, it was really fast for me to plug those numbers in, because I had already spent the time investigating the problem, finding out what those numbers were. So I want 10 terms, that's 10 over 2, the first term was 8, the 10th term was 53. And so now it's just a matter of computing that. 10 over 2 is 5, times 8 plus 53 is 61, and 5 times 61 is 305. And if you wanted to, you could spend the time to plug in those 10 numbers and add them together and see if it really does add up to 305. So, as with anything in math, I want you to notice that you have 2 ways to get the answer. One way to get the answer is brute force. Does anyone ever use this phrase, brute force? Does anyone in here use the phrase brute force? That's basically what brute force means, is that you're not going to be clever about it. You're just going to sit there and do the work. Versus using the formula, which was here. Okay, well, number 2 is very similar. I want you all to try that on your own. You'll notice this time, how many terms are we adding together? 20. So you're a lot less likely to want to write down all 20 terms because there's so many terms there. But go ahead and spend some time getting to know this sequence. Do everything we just did. You know, write out the first few terms, verify what the common difference is, although we all already know what the common difference is, right? 2, because the common difference is the number in front of the variable. So spend some time getting to know the sequence, find all the information that you would need in order to use the summation formula. Right? In order to use the summation formula, you need to know what n is. N in this case is 20. You need to know what the first term is, so go find the first term. You need to know what the nth term is or the 20th term is, so go find the 20th term. And then plug it all in and see what you get. So feel free to work with your neighbor. I'll just walk around and answer any questions. Nice, that's what I got. That's what I meant. Great. You both have to correct this. Okay. Okay, let's compare notes. First thing that would be helpful to do is just go ahead and start writing out the terms. So if I plug in 1, so 2 times 1 is 2 minus 1 is 1. Plug in 2, 2 times 2 is 4 minus 1 is 3. Plug in 3, 2 times 3 is 6 minus 1 is 5. And already I can tell my sequence is just the odd numbers, 1, 3, 5, 7, 9. I'm going to add up all my odd numbers until I get to the 20th term. Now, how hard would it be to find the 20th odd number? Not too bad. 1, 3, 5, 7, 9, 11, 13, 15, 17, 19, 21, 23, 25, 27, 29, 31, 33, 35, 37, 39. Did anyone get 39 as the 20th odd number? So that wasn't too bad to verify that my 20th term is 39. Now that was by counting on my fingers. How would we really do it? Well, we'd say that in this problem, the common difference is 2, and the first term is 1. So the first thing I need is actually to find the 20th term. So I'd use my formula, a sub n equals a sub 1 plus d times n minus 1 to find the 20th term. So a sub 20 is the first term plus the common difference of 2 times 20 minus 1. Sorry, my first term was 1. Which is 19 times 2 is 38, plus 1 is 39. So either way you do it, you end up with the 20th term is 39. Whether you just count it out by brute force or by using your a sub n formula, you get the last term is 39. Now we're in a position to do our summation formula. So the sum of n terms is n over 2 times the first term plus the last term, which in this case, the sum of 20 terms is 20 over 2 times the first term, which is 1, plus the last term, which is 39. And all of this you can do in your head. 20 over 2 is 10, and 1 plus 39 is 40, and 10 times 40 is 400. So the final answer is 400. So there's actually 3 ways you can solve this problem, maybe more. The first way would be brute force. You just sit there and type on your calculator 1 plus 3 plus 5 plus 7 plus 9, and you just keep on adding together. Nobody wants to do that. The next way is what the formula wants us to do, and this is what you'll need to show me on the test. Is show me how to use the summation formula. Use S of n equals n over 2, a sub 1 plus a sub n. The third way to do it is to be like Gauss. So what if Gauss had seen the problem 1, 3, 5, 7, 9, all the way up to 33 plus 35 plus 37 plus 39. How would Gauss have done this problem? What would Gauss do? And let's just presume that you know that there are 20 terms. So how would Gauss have cleverly added this together? Add the first and the last term. So 1 plus 39 would just be 40. And then second and second to last term. So 3 plus 37 is also 40. And then third and third to last term, 5 plus 35 is also 40. And so you can tell by adding the first and the last term, and then the second and second to last term, that you're always getting 40. And if there are 20 terms, how many pairs are there? Just 10 pairs. So you know that you're going to have 10 40s. And 10 times 40 is 400. Notice that the Gauss method is the formula. The formula, n over 2 times first plus last, is the Gauss method. This formula literally is the Gauss method because that's the first term, that's the last term. That was what Gauss noticed, that if you add the first and the last and the second to last. And then there are n terms, so how many pairs are there? N over 2. The number of terms divided by 2 is the number of pairs. So you can tell here that since this is the number of pairs, that the arithmetic sequence formula is the method Gauss uses to solve the problem. Maybe that makes you feel like, Gauss, now I'm less impressed by you, Gauss. You just used the formula. But I mean, he was 5 and he came up with it on his own, so I suppose that's still okay. Good job, Gauss. All right. Well, that's that. How about this next one up here? Does that look like another arithmetic sequence? How do we know if it's arithmetic or not? What should we do first? What? Yeah, just write out the first few terms. Always spend a little time just writing out the first few times and getting to know the sequence. So let's go ahead and look at it. We're only going to do 5 terms. Oh my goodness, with 5 terms, couldn't we all solve it by brute force? 5 terms is not very much. We could all solve it by brute force. So now let's write out the first few terms. So 3 halves to the 1, 3 halves to the first power, plus 3 halves to the second power, plus 3 halves to the third power, plus 3 halves to the fourth power, plus 3 halves to the fifth power. So altogether, that's not that bad. We could just type this into our calculator. And in fact, what's 3 halves as a decimal? 1.5. I mean, this would be so easy to do by brute force on your calculator. 1.5 to the first plus 1.5 squared plus 1.5 cubed plus 1.5 to the fourth plus 1.5 fifth. I wouldn't be surprised if someone in the room is already done. Right? Like, you just type it in your calculator, you can already be done. You can say, Mr. G, move on to the next problem. I'm already done. But we don't just want to do it by brute force. We want to see how to do it with our formula. So let's spend some time getting to know. I might have to erase a little bit. Let's get to know this new formula for the, oh, we didn't even say yet. Is it arithmetic or geometric? It is geometric because we're multiplying every time. What are you multiplying by every time? Like to get from 3/2 to 3/2 squared, what did I just multiply by? To get from, let's just write out the terms. The terms are 3/2, and then the next term is 9/4, and the next term is 27/8, and the next term is 81/16, and the next term is 243 32nds. What am I multiplying by every time? By 3/2. We're multiplying by 3/2 because on top you multiply by 3, on bottom you multiply by 2, on top you multiply by 3, on bottom you multiply by 2. So in fact, this is a geometric sequence, and our common ratio is 3/2. So just by looking at the sequence and looking at the terms and asking, what am I multiplying by every time? We see that we're multiplying by 3/2. So it is a geometric sequence. We are allowed to use this formula. And by brute force, we already essentially have the answer to the problem just by typing it into our calculator. But let's go ahead and use the formula. The formula is S of n equals the first term times 1 minus r to the nth all over 1 minus r. Now, in this problem, there's a lot of fractions. If you write it out legit, the first term is 3/2 times 1 minus r, which is also 3/2, to the power of n. N is how many terms there are. That's 5. So that's 3/2 to the 5th, all over 1 minus 3/2. Look at all of those delicious fractions. Can you do all that on your calculator? Sure. I mean, that is what we're about to do. We're about to do it all on our calculator. I don't think anyone in the world would expect you to take that and actually do it all in fractions. Like, just to demonstrate how absolutely terrible that would be to do in fractions, you'd have 3/2 times 1 minus 3/2 to the 5th, which I actually don't know what that is. 3/2 to the 5th, that'd be 2. Oops. That'd be 729/64 all over 1 minus 3/2. Okay, no one expects you to actually do all this fraction work. Because from here, I need to find a common denominator. So I'd have 3/2, and then that's 64/64 minus 729/64. And then on the bottom, 1 minus 3/2, find another common denominator. That's 2/2 minus 3/2. And then in the top, we'd have 3/2 times 64 minus. So nobody's writing this down, right? Because no one is expected to do this. Negative 665 over 64, all over negative 1/2. And then you could multiply the numerator. So you'd have 3 times 665, which is negative 1995, all over 128, all over 1/2. So then that's negative 1995 over 128 divided by 1/2, which is really negative 1995 over 128 times the reciprocal, which is 2 over 1. And so 2 goes into that 64 times. And then you have negative 1995 over 64. Whew. Okay. So again, that's just a very long, laborious process of doing everything in terms of fractions. Now, by the way, what decimal is that? 1995 divided by 64.
It's G.
Yeah.
You missed
Oh, I did miss the or the negative.
Yeah.
Is that what you're about to tell me?
Yeah.
Thank you. All right, so that's 1995 divided by 64, which is 31.171875. And then if I hit my math frac button on my calculator, that takes me right back again to 1995 over 64. Okay, so I have this answer. And you're saying, okay, well, Mr. G, if I don't have to do it that way, which way can I do it? Well, you could just immediately convert the 3/2 into a decimal if you wanted to. So you could do 1.5 times 1 minus 1.5 to the power of 5, and then divide by 1 minus 1.5. That's one way to type it in your calculator. The problem is that it might not be a fraction that's easily convertible to a decimal. 3/2 is 1.5. What if it had been 2/3? That would have been 0.6666666. How many sixes do you include? So everybody, I want you to practice putting this into your calculator the right way. And so your sum would be parenthesis 3 divided by 2, parenthesis, 1 minus, parenthesis 3 divided by 2, parenthesis, caret 5, parenthesis, divide by, parenthesis, 1 minus, parenthesis, 3/2, parenthesis. I want all of you to practice typing that into your calculator. Part of practicing this is not just the act of typing all this into your calculator and knowing where the parenthesis button is, which, my goodness, you all should know where your parenthesis button is on your calculator. But it's just appreciating, gosh, are all those parentheses really necessary? And the answer is yes. Because you need a massive, maybe I could do this in a color. I need a set of parentheses to mark out the numerator. That's my numerator parenthesis. And then I need a parenthesis to mark out the denominator. So there, maybe that's a little better. My red parentheses are telling my calculator what my numerator is. My blue parentheses are telling my calculator what my denominator is. Of course, I'm dividing my numerator divided by my denominator. And then in the numerator, I had the fraction 3/2 times 1 minus the fraction of the 5th. So all those parentheses are necessary. And then at the end there, 1 minus 3/2. The rule is to always put fractions in parentheses. Okay? So absolutely, everybody in the room, try typing that in. Parenthesis, 3 divided by 2, parenthesis, 1 minus, parenthesis, 3 divided by 2, parenthesis, divided by 5, parenthesis, divided by, parenthesis, 1 minus, parenthesis, 3 divided by 2, parenthesis. Uh-oh.
I got 19.7.
I got 19 as well. What did I do wrong?
I actually, when I was looking at that, I think.
What did I do wrong? Well, you know what I'm going to do first is actually do the brute force method to find out what the actual answer is. The actual answer is 19.7. So therefore I must have done something wrong over here. Oh, because I did do it wrong over there. The very first thing I wrote down. How sad is that? The very first thing I wrote down right here was wrong. So that made all my chain of reasoning with all those fractions wrong. I'm sure glad nobody wrote that down. My last term was just 243/32. So that's what I should have had, and now all that is wrong. But it was a very good learning lesson. Oh boy, I learned so much from that. All right, so did you all type that in, and what did you get? Did you get 19.78125? And just as important, do you know where your math frac button is? Math frac is easy to say and fun to use. You go to the math button, and then the first option says frac, enter, and it gives us the answer 6:33:30. Speaking of brute force, the other way that you could have brute forced this problem, imagine if you took the fractions 3/2 plus 9/4 plus 27/8 plus 81/16 plus 243/32. How do I add all those fractions together? What would you need to find? Common denominator. Oh man, could you even imagine? So you'd have to sit there and find a common denominator. Multiply that by 2 on top and bottom, multiply that by 4 top and bottom, multiply that by 8 top and bottom, multiply that by 16 top and bottom, and then you'd have all of that, which I guess is 48/32 plus 72/32 plus something 108/32 plus 162/32 plus 243/32. And then that would all add up to 633/32. So that's just yet another way that you could do it. One reason I show you some, well, you tell me, why do I show you so many ways to solve one problem?
You have options.
Yeah, you have options. I was hoping no one would say because you hate us. That's not true. I show you lots of options because I love you. Because I want you to see that you have a flexibility of methods that you can use to solve a problem, and that you can always try something, right? Like, would there be any reason to leave this problem blank on the test? There'd be no reason to leave that problem blank, because you could always do it by brute force, you could do it on your calculator, you could do it by hand, even if you forgot the formula, which I'm going to write on the board. Right, so I'll give you these formulas on the board on the day of the test. Okay, all right. As always, I'm sure you're all saying, Mr. G, your phone went off a while ago. Just stop talking for a little bit. And the time is 9:06, so let's all be back at 9:16. All right. Who was? Oh, that poor girl. Okay.
She texted me.
Morning, Kevin. Kevin, do you have the packet for chapter 9? This is your practice final. Oops. Oh, man, sorry. That was almost going to be really cool. I'm going to try it again. Boom. That was my goal. Mm-hmm. Oh, yeah. Yeah, absolutely. That's a great idea. Of course, knowing that practice final is very important. Yeah. It's not necessarily in chronological order, but it's only 20 questions. It's fairly short. I think it's only 3 pages. So it might skip around a little bit, but it's generally in order.
All right. So we have a few more questions to look at, and then we can talk about your test and final exam. So in number 4, 5, and 6, they're telling us the formula. I'm sorry, they're not telling us the formula. They're just telling us the terms. That's it. So we don't have a formula for the explicit formula. We don't have an implicit formula. All they've done is given us the first. So you've got the first term, the last term, and then they've given you a few terms. No problem. So this leaves a little bit to be desired. We want to add these things up. What method could we immediately use? Brute force. Yeah, we can just brute force these problems. It would be unfortunate though, right? Like, so let's look at this first one. 1, 4, 7, what's my common difference? 3. And we're adding 3. So does anyone want to add by 3 up to 295? No. No, definitely not. So 1, 4, 7. Keeping on adding by 3, that'd be 10, 13, 16, 9. Could you do it?
Yes.
Yeah, you sure could. And if you're on an airplane and you have nothing else to do, you might even enjoy it. Right? So we need to get all the way up to 295. Well, we don't want to do that by brute force. We do want to find the sum in any case. Is this arithmetic or geometric? It's arithmetic. Okay, so we know that we can use the formula S of n equals n over 2 times the first term plus the last term. And again, you might find it helpful to always think of this a sub 1 plus a sub n as the first term plus the last term. Because in that case, what do we already know to plug into the formula? And we already know the first term, and we know the last term. What don't we know? How many terms there are? Well, now this is, what's that?
Should be easy because we got 1 and 295.
It should be easy, what, to find out how many terms there are? Yeah, so how many terms are there? You think 95?
2.
Oh, what, are there 295 terms?
No.
Yeah, so how many terms are there? How can we find that out? How many terms are there? In other words, how many times am I adding 3?
Okay, you divide 295 by 3 because you know they increase by 3.
Are these terms necessarily divisible by 3? In fact, none of them appear to be divisible by 3. So dividing by 3, I don't know will work. It's an interesting idea, Annabelle. You might get somewhere close to the approximate answer, dividing by 3. But what do we do?
The first one, the last one, and divide by 2.
Maybe you add the first one to the last one and divide by 2? If you add the first one to the last one, why divide by 2? Oh, okay, because you're doing the pair thing, the Gauss thing. Well, that's true that we are adding the first plus the last and the first plus the last, but that's telling you the sum of the first and the last term. It's not telling you how many pairs there are. So we don't know how many terms there are. We don't know how many pairs there are. One thing that we could think about is the fact that going from 1 all the way up to 295, we are adding 3 over and over and over again, right? Now, I could say, how many times am I adding 3? Do we know how many times we added 3? No, so I could call it x. So if I take 1 and add 3 x times, I should eventually get to 295. Right, so now we just solve for x, and that will tell us how many times we added 3. Does that seem reasonable? So solving that real quick, and one, this was close to what you suggested, we can do 295 minus 1, which is 294, and now that number is actually divisible by 3, and we get 294 divided by 3, oops, 294 divided by 3 is 98. Now, is 98 the number of terms? What does 98 represent in this case? It's the number of times I added 3. So how many actual terms is that? Like, just look at the beginning. How many times did I add 3? 1 to 4 and 4 to 7. So I only added it twice, but how many terms are there? 3. So if I added 399 times, I'm sorry, 98 terms, then how many terms are there? It would be 99. Does it make sense? That the number of times you add 3, like try another example. If I just look at 5 terms, how many times did I add 3? Once, twice, 3, 4 times. So the number of times you add 3 is only 4 times, but the number of terms is 5. So the number of terms is always 1 more than the number of times you added the common difference. So if this is 98, now we can say that there are 99 terms. So now I know that n equals 99, which means the sum of 99 terms is 99 over 2 times 1 plus 285. Now, the reason I showed that to you is just so you can appreciate the understanding behind figuring out how many terms there are. Right? Because we said, well, I don't know how many terms there are, but I'm adding 3 over and over and over again. So if I take the first term and add 3 x times, I should eventually get to 295. And that tells me how many times I added 3. And so the number of terms is 1 more than that. And so the number of terms is 99. You can either walk yourself through that chain of reasoning every time, or you can just use a formula. And I think we actually derived this formula last time. If you recall the nth term formula, a sub n equals a sub 1 plus d times n minus 1, we can just solve for n. And that's what we did last time. So solving for n, I moved the a sub 1 over a sub n minus a sub 1. And then I divide off the common difference d. So that's so far a sub n minus a sub 1 over d equals n minus 1. And then I add the 1 over, and that gives me that n, the number of terms, is a sub n minus a sub 1 over d plus 1. And this is actually a very valuable formula that's worth memorizing. That's the formula that tells you how many terms there are. And notice, is this what we did? I did the last term minus the first term, so 295 minus 1, which is 294. And then what? I divided it by the common difference, 3, to get 98. And then what did I do? I added 1 to it. So the formula is reasonable and it works. So you'd want to write down that formula as one more formula that we have to memorize. So for an arithmetic sequence, n is equal to the last term minus the first term over the common difference plus 1. All right, well, so now we're ready to actually just compute this. You'll notice that 99 divided by 2 is 44.5. You might say, uh-oh, 44.5. This sum has to be a whole number. How can I have a 44.5 in there? But the 44.5 is going to balance out with this term right here, and the decimal will go away. So what do we have then? We have 44.5 times 296, and that equals? Sorry, that's 49.5. So 49.5 times 296 is 14,652. Is that surprising? Is that really the answer? My goodness, that's a big number, isn't it? I mean, look, we're only adding up numbers that go from 1 up to 295. Do you feel like adding those numbers together, you get all the way up to 14,000? I mean, maybe it's just me that 14,000 seems like a lot. If I offered you a job in which I paid you $1 on the first day and $4 on the next day and $7 on the next day, all the way up to $295 on the last day for 99 days in a row, which is roughly over 3 months, would you take the job? I mean, maybe. So that would be $14,652 divided by 3 months, and then times 12 months in a year, that'd be $58,000. Not bad. I mean, I don't think too many people would shake a stick at a yearly income of $58,000, especially coming out of high school or still in college. $58,000 is good. So this is reminiscent of a problem that we'll see in a second, where someone offers you a job for a very small amount of money on the first day, but over time, your amount of money builds over time, and would you take the job? This is an old riddle. Okay. Done with that problem. How about this next one? What's happening here? Yeah, the numbers are going down. What's the common difference? Yeah, -2. We're subtracting by 2 every single time. And we're going all the way out to -146. Right off the top of your head, is the answer going to be positive, negative, or 0? It's going to be very negative, right? Because we only had 2 positive terms to begin with. And they'll very quickly cancel out with negative terms. And so those terms all cancel out. And what we really have is -6 plus -8 plus dot, 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 all the way up to -146. So definitely the answer is going to be negative. That's the kind of thing you can do right up front to just kind of guide yourself to say, okay, well, I know the answer is going to be negative. Now what can we say? So is this an arithmetic sequence or a geometric sequence? Definitely arithmetic because we're adding my -2 over and over. So my common difference is -2. I know my first term is 4. I know my last term is -146. I'd like to add it all together. In order to do that, we need our sum formula. S of n equals n over 2 times the first term plus the last term. So do we have all the information we need? I know the first term, I know the last term. What's n? Once again, we don't know what n is. So before we can do anything, we need to calculate how many terms are in the sequence. Do you know how many terms are in the sequence just by looking? No, because there's a dot, dot, dot right there. I have no idea how far that goes. Would you want to do it by brute force? No, that's a very long ways to count by 2. To count by 2 all the way up to 146, that's a long way. So instead, we can use this formula we just came up with. Last minus first divided by the common difference plus 1. So last minus first divided by the common difference plus 1. That will tell us how many terms are in that sequence. And again, you might want to write that down in words. N equals last minus first all over d plus 1. So our last term was -146 minus our first term, which was 4, all over the common difference, which is -2, and then plus 1. Now, folks, everyone in here, well, at least I presume you all have a calculator. So you should all be able to do this computation correctly. Just taking a guess, if you just grabbed an American off the street and gave them this computation to do, even with a calculator, do you think they're going to get it right? Maybe, maybe not. There's a lot of negatives in there, and people make mistakes with negatives, unfortunately. So if you were to type that into your calculator, what would it look like? Parenthesis, -146 minus 4, parenthesis, divide by parenthesis, -2, parenthesis, plus 1. That's what it should look like on your calculator. Did anyone get 76? Anybody else? 76? Okay, 76. So now we can calculate our sum. The sum of 76 terms is 76 over 2 times the first term, which was 4, plus the last term, which was -146. So that's 38 times -142, which is -5396. And is our answer negative like we thought it would be? Yeah. All right. Last problem on this page, number 6. Is that an arithmetic sequence or a geometric sequence? This one's geometric. What are we multiplying by every time? Yeah, we're multiplying by half. It might be easy to make the mistake that you're multiplying by 2 every time. And you are multiplying by 2 in the denominator. But the number that you're actually multiplying by If you go from 1/2 and you have to equal 1/4.
Sorry, Annabelle.
Sorry. Then you multiply times 1/2. Did it say sorry, Annabelle?
Yeah.
Wow, it knows your name and everything. This is a brave new world. Okay, so yeah, we're multiplying by 1/2 every single time. So our common ratio is 1/2. Now, we want to find the sum. It's geometric. Now what do we do? The other aspect of math, so the art of mathematics, is figuring out what to do next. Isn't that always the tricky part? Figuring out what to do next. What do we do next? Sometimes it's helpful just to think about what we know. This is it's a geometric sequence. We're multiplying by 1/2 over and over again. And it's a geometric sequence. We want to add them all together. We have a formula, right? So we have a formula, S sub n. Let's look at that formula. S sub n equals the first term times 1 minus r to the n all over 1 minus r. What do we know from the formula? Do we know a sub 1? Yeah, a sub 1 is the first term, which is 1/2. Do we know r? Yeah, r is 1/2. Do we know n? Do we know how many terms there are? We don't. So how do we know the number of terms? Do we do brute force to find the number of terms? Do we do brute force? We can do brute force because if the first term is 1/2 and then a 4th, we're multiplying the denominator by 2. So that's an 1/8, a 16th, a 32nd, a 64th, a 128th, and a 256th. So brute force wasn't that bad. I naturally assume you've all been practicing multiplying by 2s, just like I mentioned at the beginning of the semester, right? When you're standing in line, waiting for your food, all that. So that wasn't that bad. How many terms are there? 1, 2, 3, 4, 5, 6, 7, 8. So n equals 8. So the brute force method was not that bad. Now you might say, what about a formula? Is there a formula for n? Well, how did we derive this formula for n? To derive the arithmetic formula for n, we started with the explicit formula, and we solved for n. So that wasn't bad, we just solved for n. What's the explicit formula for a geometric sequence? It's a sub 1 times r to the n. R to the n minus 1. And so here we want to solve for n. Where is the n located? In the exponent. Therefore, you would need a logarithm to solve for n. So if we wanted to solve for n, you divide off the a sub 1, and that gives you a sub n over a sub 1 equals r to the n minus 1. And you want to get that exponent out, so you'd have to do a logarithm. So you'd say log base r of a sub n over a sub 1 equals n minus 1. And therefore, n is equal to log base r a sub n over a sub 1 plus 1. Folks, no textbook teaches this formula. Nobody uses this formula. Problems like this are always expected that you do it by brute force. But that is the formula, right? So could we do it? Could we try it? I mean, we already found by brute force the answer was n equals 8. But could we do brute force? This is saying that n is equal to log base r, which is log base 1/2, of the last term, which is 1/256, divided by the first term, which is 1/2. Can we compute that? Of course we can. It's possible to compute. You just have to very carefully do it on your calculator. You'd have to do the change of base rule. So that'd be log of 1/256 divided by 1/2 divided by log of 1/2 and then plus 1. And you type all that in your calculator and you get 8. But I'm going to go ahead and tell you, you don't necessarily need that formula. In a problem like this, you could do by brute force. At least I've never done a problem in my whole life where I actually use that formula, because I've never even seen that formula in a textbook. So we just did that problem already by brute force. So n was 8. So now we plug everything in. So the sum of 8 terms is the first term, which is 1/2, times 1 minus the common ratio, which is 1/2. N is 8. all over 1 minus a half. So what's so exciting about doing this computation on your calculator? All the parentheses you need to use, right? First of all, did I type that in correctly? Was the first term a half? Yeah, and then 1 minus a half to the 8th, all over 1 minus a half. So what will the parentheses look like here? You'll need a numerator parenthesis to say 1 half parenthesis times 1 minus a half to the 8th parenthesis. That's just the numerator. And then divide by, and then you need your denominator parenthesis, which is 1 minus a half. So everybody try plugging that in to your calculator and see if you get the right answer. First of all, is that correct? Numerator parenthesis, divide by denominator parenthesis. So in the numerator, I have 1 half times 1 minus a half to the 8th, yeah, all over 1 minus a half, yeah. Now, since 1 half is so easy to do as a decimal, couldn't we have also done, we could have just done 0.5 times 1 minus 0.5 to the 8th divided by, and then I presume everybody can do 1 minus a half in their head, which is 0.5. There. So could you type it in that way with decimals instead? This time you could, because 1 half was easy to do as a decimal. What answer did you get? Anyone want to share? What did you get?
256.
What is it?
255 over 256.
255 over 256? Ah. That sounds right. Did anyone else get that? Yeah. Which is about 0.99999. And remember, we did this problem the other day to infinity. We said if you add a half is 4 plus an eighth all the way to infinity, what does it add up to? 1. Yeah, 0.9999999, which is 1. Okay. Let's say we're all done with those. And is that it, by the way? Is that the end of the packet? These problems right here? Oh boy, oh boy. So here we are. We've got about an hour left to go. And we get to close class with everyone's favorite word problems. Okay. How do we solve the first one? Find the partial sum. By the way, that's just the phrase, that's just the vocabulary, partial sum. Partial meaning S sub 11, so you're going to add the first through the 11th terms. It's a partial term, partial sum. It's not like the sum of all of infinity terms. It's just the terms 1 through 11. So find the sum of 11 terms for the arithmetic sequence with A is equal to 3. In that terminology, they're implying that that's A sub 1. So you might want to put that in there. It's really A sub 1. Well, the first term is 3 and the common difference is 2. So they're saying to add those up. Everyone go ahead and give that a whirl. I want you to add up 11 terms in the sequence where the first term is 3, the common difference is 2. You can do it by brute force, but you should really use the formula. And what are you going to do first? You're just going to spend some time getting to know the sequence. Right? Go ahead and write out the first few terms. Get to know the sequence. Look at some terms, see what it looks like. Start jotting down all the information that you know. Write down the formula for the sum. And then see if you know all the information to put into the formula. Start looking for that information. Then in the end, you'll have all the information you need to plug into the formula. That's 9. All right, let's get to know this sequence together. The first question we want to know is it arithmetic or geometric? Because we need to know if it's arithmetic or geometric in order to decide what formula we get to use. So is it arithmetic or is it geometric? How do we decide? We just start writing out the first few terms. So what's our first term? 3. And then what do we start doing? Add 2. So 3 plus 2 is 5, plus 2 is 7, plus 2 is 9, plus 2 is 11. And so on up for 11 terms. Now in this case, we could go ahead and write it down. 1, 2, 3, 4, 5 terms. So it'd be 6 terms, 7 terms, 8 terms, 9 terms, 10 terms. Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there, just by brute force, I went ahead and just wrote down all 11 terms. Now, our goal is to find the sum. And since this sequence is arithmetic, what formula will we use? The arithmetic formula, so S of n equals n over 2 times a1 plus an. So we jotted down the sequence. We got to know it a little bit. We saw that it was arithmetic. We saw that the common difference was 2. Now we wrote down our formula. And we ask ourselves, well, I need to know what n is. So what is n? How many terms are there? 11. So n is 11. The first term, do we know that? It's 3. The last term, do we know that? 23. So we do know all the information we need to know. But we did do brute force. To be fair, how would you find the 11th term normally? You'd have to use your explicit formula, a sub n equals a1 plus d times n minus 1. If you wanted to know the 11th term, you'd have to plug in the first term is 3, plus the common difference is 2, and that's 11 minus 1. So that'd be 2 times 10 is 20, plus 3 is 23. So to find the last term, you either do brute force and find the last term, or you use your nth term explicit formula to find the last term. Either way, we've got 2 different methods for finding the last term. Now we can go ahead and find the sum of 11 terms, which is 11 over 2 times the first term plus the last term. Which is? Did anyone get 143? Now, could you have gotten that answer by brute force? Sure. You could have just added 3 plus 5 plus 7 plus 9 all the way to 23. If you really wanted to make sure you got the answer right on the test, could you check your answer by brute force? Sure. And then you know for sure you have the right answer before you turn in your test. Okie doke. Now that you just saw how to do this one, try number 8. You're going to do a partial sum for the geometric. They just come right up and tell us it's geometric. They give you the first term as 6, and they give you the common ratio as 2. So in general, what are you going to want to do right now? Go ahead and write out the sequence. Wouldn't hurt to go ahead and write out all 8 terms. And then write down the formula you're going to use and see if you have all the information you need to plug into the formula. All right, so how do we start? We just get to know the sequence by writing it out. Our first term is 6, and we start multiplying by 2. So 12, 24, 48, 96, 192, 300 and something. 384. 1, 2, 3, 4, 5, 6, 7. One more term, 8. Are those all the terms? Did anyone else write them all down? We can, since it's such a short sequence. We want to add them up, so you can go ahead and type that into your calculator, find out what the answer is. But so what do we want to do? We want to do that was close. That was the closest I've ever been to falling. All right. So the sum is the first term times 1 minus r to the n all over 1 minus r. So do we have all this information? We know the first term is 6. We know the common ratio is 2. And we know the number of terms is 8. So yeah, actually we already know everything that we need to know. So we can just plug it all in. So we've got the first term, which was 6, times 1 minus the common ratio, which is 2, to the power of 8, all over 1 minus 2. And again, typing that all into your calculator. Now, you don't have to type it all into your calculator at once. You can always find each little bit, 1 bit at a time. And I also encourage that a lot, is that just find each part. So what's just 1 minus 2 to the 8th? 1 minus 2 to the 8th. It's just negative 255. So see, you don't always have to type everything in your calculator all at once. That's a big temptation, but it often leads to a mistaken answer because it gets typed into the calculator the wrong way. If you just do one little piece at a time, then you can just say, well, a negative divided by a negative is positive, and all that's over 1, so it's just 6 times 255, and by just being slow and careful, you get 1530. So what do you got? And again, you could type the original sequence into your calculator and see if you get 1530. All right. Finally, they gave us an infinite sum to do. We want to do an infinite sum where the first term is 2, and we're multiplying by 2/6. Now, folks, what's 2/6? What does it simplify to? Yeah, it's really a third. So, I mean, I hope, let's not do this whole problem using 2/6. Let's do this whole problem using 1/3. That's a little easier. Now, what are we going to do? Let's write out the sequence. If the first term is 2, which is really 2 over 1, why do I write it as 2 over 1? Because we're going to start multiplying by 1/3, and when you multiply a fraction by a whole number, it's helpful to make that whole number a fraction. So 2 over 1, here I'm going to do some scratch work. 2 over 1 times a third is 2/3. So I know my next term is 2/3. Now 2/3 times 1/3 is 2/9. So I know my next term is 2/9. And then 2/9 times 1/3 is 2/27. So I know my next term is 2/27. Now at this point, if you just wanted to keep writing it out, obviously the numerator is always going to be 2. And you're really just multiplying the denominator by 3 over and over again. So when you say the common ratio is 1/3, what you're really saying is multiply the denominator by 3 over and over and over again. So then that would be 81, and then 243, and so on. And so we're asking, what happens when we add that all up? You could type it into your calculator and start adding the terms up to see what the answer is close to. But in the end, you just need to write down the formula, which is the sum of infinitely many terms is the first term over 1 minus r. Isn't that a nice, simple formula? So in this case, the first term was 2, and the ratio is 1/3, so that's 1 minus 1/3. And you can feel free to do that calculation any way you like. You could just type it all into your calculator. That would be 2 divided by parenthesis 1 minus parenthesis 1/3 parenthesis parenthesis. Or you could say 1 minus 1/3 is 2/3, so that's 2 divided by 2/3, which that's 2 times 3/2, which cancels the 2's and you get 3. But doing it on your calculator the other way. Did everyone get the answer of 3? Okay, so the answer is 3. Now keep in mind, we just added together an infinitely long sequence. So this presumes that you typed in all infinitely many terms and added them all together. The answer really is 3. The answer is not 2.99999999999. The answer actually is 3. If you finish, well, you can never finish adding together infinitely many terms. But if you could finish, the answer would be 3. All right. Number 10 is a really good problem. I know. I say everything is a good problem. But it is a good problem because it requires us to really visualize what's happening. And that's a critical skill in mathematics, is just to visualize what's happening. So it says, determine the seating capacity of an auditorium with 10 rows of seats. So first of all, how many rows of seats are there? 10. Right? I mean, that was an obvious question, but we have an auditorium with 10 rows. So just imagine, here's the stage. Presumably there's a stage. And then you've got seating, so first row, second row, third row, fourth row, 5, 6, 7, 8, 9, 10. Can everyone see the theater? Like, that's what the theater looks like? It's a pretty small theater, right? Only 10 rows. That's a very cozy environment. You invite your mom and dad to see the forum. Anyone? All right, so there's our theater. And there are 20 seats in the first row, 22 in the next row, 24 in the next row, and on and on and on. And I can't help myself. See, brute force, another word for brute force is just draw a really good picture. If you just draw a really good picture of the situation, you can almost always solve the problem by brute force if you just have a really good picture. Because at this point, what are they asking? Determine the seating capacity. So what does the phrase seating capacity mean? Yeah, how many people can go there? Now, of course, we're not supposing they're standing room only. Like if you're allowed to fill more people in by standing in the back, that doesn't matter for our answer. We want to know how many people can sit. So you could easily just add those up on your calculator and you'd be done. But we don't want to do it by brute force. We want to do a formula. So we're trying to find the sum of an arithmetic sequence. What formula are we going to use? Yeah, the very first one. Now, I already presumed that it's arithmetic. Is this arithmetic? Because we're adding 2, adding 2, adding 2. Okay, so we're going to do S of n equals n over 2 at first term plus last term. And so how many rows are there? Oh, 10 rows. They told us that in the beginning. there are 10 rows, so that's 10 over 2. The number of seats in the first row is 20, and the number of seats in the last row is 38. Now recall, I got that number 38 by brute force. So had this been an auditorium with 1,000 rows, I wouldn't have done that by brute force. I would have found the number of seats in the last row by actually using my explicit formula. And I would have said, how many seats are in the 10th row? Well, the first row was 20, the common difference is 2, and it's 10 minus 1 is 9, and so then that's 38. So the explicit formula gives me 38, just like my really good picture gave me 38. And our answer is 290. Now, a problem like this, folks, is there any reason to leave a problem like this blank? No, no reason to leave this problem blank. You can always just draw a picture, see what's happening, do the problem by brute force. Have you ever used this phrase, brute force, before? Maybe you have, maybe you haven't. I don't know why I'm only saying it now, towards the end of the semester, but brute force is a great method. It's not how Gauss solved the problem. Did Gauss solve his problem by brute force? No, he used a clever trick. He used a formula. But brute force is still, it'll get the job done. Okay, so this problem right here, suppose you go to a company that pays 3 cents on the first day, 6 cents on the second day, 12 cents on the third day. First of all, do you want to take this job?
No.
Right, yeah. How many of us want to take this job? But just so you know, there's an old riddle. And I want you all to see this riddle. Riddle paid chessboard. Wow, search engines are so wheat and chessboard. Well, I'm trying to find the original riddle, but I don't see it. Chessboard riddle? Maybe I should do that. Well, I don't see it. All right, well, the original riddle, which comes down to us from time, is that you're in a kingdom, and some peasant, normal person, does a huge favor for the king. And the king says, oh, how can I repay you for this act of service to your country? And the peasant says, oh, I don't need much, king. How about you pay me a penny today, 2 pennies tomorrow, and keep doubling the number of pennies you pay me until the end of the month. And that's all he asks for his reward. So 1 penny, then 2, then 4, then 6. I'm sorry, 1, 2, 4, 8. And so the king agrees, because the king doesn't understand geometric sequences. And he says, sure, I'll pay you a bunch of pennies. And so how much money did the peasant get by the end of the month? If he gets a penny, and then 2 pennies, and then 4 pennies, and then 8 pennies, all the way up until the 31st day of the month, presuming that there are 31 days of the month, how many pennies did he get on the last day? And how much money is that if you add it all together? So this was the original riddle. And so we would find the sum of a geometric sequence for the first term, and then 1 minus r to the n, all over 1 minus r, where the first term was just a penny. And then we're doubling, so r equals 2, so it's 1 minus 2 to the number of times you're doing it is 31 times, so 31 days in a month, all over 1 minus 2. And so that gives us 1 minus 2 to the 31st, all over -1. And so what is that? That's the sum of all the pennies that this peasant is going to earn from the king. So 1 minus 2 to the 31st is, all divided by -1, that's 647, 483, 147, and 2. So that's 100,000 million billion, 2 billion pennies, which if you just move the decimal twice, then move all of your commas, that was a total of, what is that? 100,000 million, $21 million. So pretty good deal, $21 million. Obviously, the king had to turn over the entire kingdom to the peasant, and the peasant became the king. And that was the end of the riddle. Okay, so likewise, back to our problem. You go to a company, it's going to pay 3 cents on the first day, 6 cents on the next day, 12 cents on the third day. And if they keep doubling it, what will be your income for 29 days? First of all, just from listening to the problem, would you take a job that only paid 3 cents on the first day? No. But now that you know the riddle, would you take this job? In a heartbeat. Because first of all, how much are they giving you on the first day? 3 pennies. I mean, that's more than the peasant in the riddle. The peasant in the riddle only got 1 penny on the first day. You're getting 3 pennies on the first day. So this is a really good deal. I would take that job immediately. So how do we solve it? We want to find the sum of how many days? Well, I'm going to write down the formula first. A sub 1, 1 minus r to the n over 1 minus r. So how many days are we doing this? 29. So we're finding the sum of 29 days worth of income. The first day was 3 cents. And then 1 minus, and we're doubling the money, right? 3, 6, 12. We're doubling the money. So that's 1 minus 2 to the 29 all over 1 minus 2. It'd be kind of fun if the next time you have a job interview, ask to get paid this way. Just see what the person says. Hey, what's your pay structure? You get vacation? Here's how I'd like to be paid. So what do we got then? 1 minus 2 to the 20. Right? Now, nobody wants to write down that huge number. It's a huge number. So you definitely would want to be able to do this whole calculation on your calculator in one step. So what would that look like? It'd be 0.03 times parenthesis 1 minus 2 to the 29, parenthesis, divide by parenthesis negative 1. And I calculated 16,106,127 and 33 cents. 100,000 million, yeah, 16 million. Now, you notice this person got 3 cents on the first day, but they only made 16 million. Whereas in the other riddle, they got 1 penny on the first day, they got 21 million. Why did the person who got 3 cents on the first day only get 16 million, whereas this person only got 1 penny on the first day, they got 21 million? Yeah, because they had more days, right? So they did 31 days, not just 29 days. Either way, I'm content with a double-digit $1 million salary. I won't argue too much. All right. Number 12, a man gets a job with a salary of $33,700 per year. He's promised a $2,500 raise each subsequent year. I would take that, $2,500 a raise per year, that's great. Find his total earning for a 10-year period. Now, first of all, just everyone, immediately, let's just say that right now, someone offered you a job for $33,000, and you get a $2,500 guaranteed raise every year from now until you retire at age, well, let's be honest, 70. Would you take the job? I mean, this seems like not a bad deal if you're getting $2,500 per year. I mean, in the beginning, you're like, yeah, but I got to spend the next few years earning in the 30s, then the 40s, then the 50s. But I mean, eventually you're going to be earning in the 60s and the 70s. And then, in fact, how many years does it take to increase your raise by 10,000? Only 4 years. So every 4 years, you have a $10,000 bump. I mean, I'm thinking that's better than most jobs to get a $10,000 bump every 4 years. So yeah, overall, this is a nice situation. Find his total earning for a 10-year period. So is this arithmetic or geometric? Are we multiplying over and over, or are we adding over and over? We're adding over and over, right? Because we're adding 2,500 per year. So now I know my common difference is 2,500. And what is it we want to do? Find his total earnings for a 10-year period. That doesn't mean find out how much he's earning in the 10th year. If you wanted to know how much he was earning in the 10th year, you would do the explicit formula and say, hey, what is he earning in the 10th year? In the 10th year, he would be earning 33,700 plus the common difference of 2,500 times 10 minus 1, which is 9. So that's how much he's earning in the 10th year. which is what? 33,700 plus 2,500. So he's earning 56,000 in his 10th year. But we want to know how much he made over the entire 10 years. So that's telling us how much he made in his 10th year. So now we can go ahead and do the sum, which is n over 2, the first plus the last. Over a 10-year period, so 10 over 2, the first year plus the last year. So in terms of our formulas, we have a few formulas to add on. We need the sum formula, which is S of n equals n over 2, a1 plus an. We also need our n formula, which is last minus first over common difference plus 1. And then for our geometric, our sum formula was a1 1 minus r to n over 1 minus r. We also had our infinite sum, which is just a1 over 1 minus r. Okay, so all of that right there is essentially what you need to know on the test. All of those formulas will be used at some point. It looks like a lot of formulas, doesn't it? What did we get for the last part of that problem? 33,700 plus 56,200 times 5. So in that 10 years, the individual made $449,500, which is almost $500,000. Yep. Okay, so folks, we have a little time on our hands. First things first, if you haven't already written that down on a single sheet of lined paper, I would write it down. Because just having all those formulas handy will help you do all of your homework on the Morse system. Second, we can talk about your practice test, which I don't have up here, and your practice final. So let's see. First of all, does anyone have any recent questions from homework? Some of you send me questions, some of you don't. But does anyone want to ask any questions from the homework right now? Since we have this time on our hands. We're in section 9. 9.1 and 9.2. Any particular questions from chapter 9 that anyone wants to ask? I don't have any in particular that I feel the need to go over with you. So just as always, folks, click that button, message the instructor, or post the question to forum, and I'm happy to help. Yeah, all those look pretty straightforward. About sigma notation. When you're doing the more homework for section 9.2, they're giving you sigma notation problems. You definitely want to show your work. Write it all down on paper, very carefully, term by term. Well, that one looks kind of fun. We might look at number 3. Ooh, we could look at number 4. Okay, let's look at a couple of these. Okay, a lot of these are just like what we did in class. So let's start with this one. A lot of math problems at first glance look hard. And so what you need to do is spend a little time with the problem. Just get to know it. See what it says. Write down some terms in the sequence. That's always a good idea. So, look at this one. It says, I'll rewrite it because it's kind of small. Sigma notation from n equals 0 up to 18 of -1 to the nth times 2n. Yep. What part about that looks tricky? Or just everything? No, not everything. Which part looks tricky? Maybe the -1 to the nth part? So what happens if you start multiplying -1 times itself over and over again? Like -1 times -1 is +1, times -1 again is now -1, times -1 again is now +1, times -1 again is now -1. So by multiplying -1 times itself over and over and over again, you're really just alternating between the values of 1 and -1, and then 1 and then -1. So let's write out the first few terms. What if I write out, so we have here the 0th term, the first term, the second term, all the way up to the 18th term. Notice that we're actually starting with the 0th term. So how many terms are there in that sequence? 19, because it goes up to 18, but you have an initial term of a sub 0. Okay, so what's our first term? I'm going to plug in 0, so -1 to the 0 times 2 times 0. Notice, I'm going to actually write this down. I'm not going to leave it to my imagination to do it. So on the one hand, what's -1 to the 0? Anything to the 0 is, anything to the power of 0 is 1. But then I'm taking it and multiplying it times 2 times 0, so that's just 0. So the first term is actually just 0. It doesn't even change the outcome of this sum. Okay, so then what about the first one? Or the first term? So now it's -1 to the 1 times 2 times 1. So what's -1 to the first? That's just -1. So this term is negative, and then 2 times 1 is 2, so that's -2. Okay, well, let's keep going. Now I'm going to find the second term. So that's -1 squared times 2 times 2. So -1 squared, that's negative times a negative is positive. So now that's going to be positive 4. Now you might say, oh no, do I have to keep on doing this the whole way? Well, no, because at some point you're going to see the pattern. So now -1 to the third times 2 times 3, -1 cubed. So that's a negative times a negative times a negative, which is, since there's an odd number of negatives being multiplied, the answer is negative. And that's a general rule. If you multiply -1 times itself an odd number of times, you end up with a negative. Whereas if you multiply a negative times a negative an even number of times, the answer is positive. So this is now negative 2 times 3 is 6. Now look at our sequence. It goes 0, 2, 4, 6. The next one would be 8. So now we have, so 0, -2, +4, -6, +8, -10, +12, -14, +16, -18, and so on. So I just had to actually do some detailed calculations for the first few terms until I saw the pattern. Now, what kind of a sequence is this? Is it arithmetic or geometric? Am I adding the same number over and over again? Actually not, because first I subtract 2, then I add 6, then I subtract 10, then I add, like, I don't know, what is that, 14? So no, I'm not adding the same number over and over again. Is it geometric? Am I multiplying by the same number over and over again? I'm multiplying by -1 over and over again because the signs are changing, but I'm not actually multiplying by the same number over and over again. So is it arithmetic or geometric? Neither. So do we have a formula for computing this sum? No, we do not. So the only method available to you? Brute force. So you'd say, okay, well then the sequence is 18. I have to go from 0 to 18. So that's the 0th term, and then first term, second term. So that's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 10 terms so far. 11, 12, 13, 14, 15, 16, 17, 18. There. Did I write down all 18 terms? Now, is this problem more about mathematical skill or more about patience?
Patience.
More about patience. Patience is a very valuable math skill. Okay, so now I take all that and I type it into my calculator. And you can do that any way you like. You can add up all the positives first, and then add up all the negatives, and then just have those two to add together. Or you can just type them all into your calculator one at a time. But as you're typing that into your calculator, you have to go plus and then minus, and then plus and then minus. Could you make a mistake while you're doing that? Yeah, very likely. So again, this question is more about patience. Okay, so that was a good one. Wait, there was one more I wanted to show you. I know the class is almost over. Here comes another good one. Write this down using sigma notation. So they're saying, you're going to do the sum of 1 plus 2 plus 3 plus 4 all the way up to 103, where you need to know what A and B are. So in this particular problem, you start with 1. Now, what are we doing in this problem? You're just adding 1 every single time, right? And so, as a matter of fact, the B term, the formula, is simply the variable n. Because the term number is the size of the term. The first term is 1, the second term is 2, the third term is 3. The formula is just n, and you're going from 1 all the way up to 103. Let's see if I got that right. Yeah, there we go. So they're asking for the formula to put into the sigma notation. Number 5 is a little more tricky because they're saying the first term is 1 over 1 times 2. And the next term is 1 over 2 times 3. And the next term is 1 over 3 times 4. So what are we saying there? Notice it's almost a factorial problem. It looks a little bit like a factorial problem. Notice now the first term is 1 over 1 times 2. The second term is 1 over 2 times 3. And the third term is 1 over 3 times 4. What matches in this case? The first term is 1 over 1 times 2. The second term is 1 over 2 times 3. The third term is 1 over 3 times 4. So what would the nth term be? 1 over n times n plus 1. Because the first term is 1 times 2. 2 is just 1 more than 1. And 3 is 1 more than 2. And 4 is 1 more than 3. So in that case, that would be the formula for this term. Let's type it in and see if it's right. So the formula would be 1 over parenthesis n parenthesis n plus 1 parenthesis parenthesis. And we're going all the way up to the 98th term because the last term is 1 over 98, so that must be the 98th term. And there we go. So that worked. Okay. So those looked a little tricky, and I think now we're done. So any questions? Did everyone pick up a practice final? I picked them up and brought them over here. Did everyone get a practice final in the room? So folks, your practice final, I would like sleep with this thing. Day in and day out. Practice every single problem multiple times until you can do it from just muscle memory, right? Because the final exam will be very similar to this and shorter. The final exam will be shorter than this. There are 31 problems on here. Final exam is only 20 problems. So start doing this practice final. Do it every day. Practice, practice, practice until it's routine. And then the final exam will be very simple for you. If you have any questions at all, please ask me. Otherwise, folks, notice that next class, which is next week on Monday, we do our practice test for chapter 8 and 9. Does everyone have the practice test?
Wait, don't we have class Wednesday?
What?
Wednesday, don't we have class?
What's today?
Today's Monday.
Oh, today's Monday? Oh, yeah, we have class on Wednesday. Sorry. Who needs a practice test for chapter 8 and 9?
What is the homework due?
The homework will be next Monday.
Next Monday?
Yeah. Who needs a practice test for chapter 8 and 9? I passed it out a while ago, but someone might not have gotten it. I have extra copies. Who wants an extra copy of the practice test? Does anyone else need a practice test? Again, this is your practice test for the chapter. Wait, you never got one. Anyone else never get one? Because I only have one left. Okay. All right, so yeah, sorry, thanks for correcting me. On Wednesday, we have class, and it's our practice day. So finish the practice test before you come to class, and we will review all those questions together. Thank you very much, folks. Yeah. Oh, yes, I will.
Mr. G, for that test, you know, that I do not need to go over with you. Does that work out?
No, you still need to. That's what the syllabus says.
Okay.
Yeah, so just find a time to come in and see me during office hours, and then we'll go. The other option I said was to, if you write out the correct solutions to every problem you missed, you can email that to me. But I would still just want even 5 minutes to just sit down.
I'll try to do that. I gotta work right now. So.
Okay, thank
I'll
you.
leave that to you. Check it out. Thank you.
Next Monday, and then following final.
Oh, good.
I don't know, that's what I'm asking.
When is the final?
Yeah.
The final's on the syllabus. It's a couple Mondays from now.
Okay,
I think it's December 10th.
so it's not this Monday coming up, the following, so 2 Mondays. from now.
You need to buy like a step stool.
Yeah.
I know. But then again, would I really want to carry a step stool with me? Yeah. No.
Carry your jug in the back. Like a foldable one.
I do carry my jug, and that's all I have the energy to carry.